Welcome to January 20th LeetCode Challenge. Koko eating bananas. Koko loves to eat bananas. There are n piles of bananas, with ith pile has piles at index I bananas. So that means that in the array piles, each pile index I has a certain number of bananas. The guards have gone and will come back in H hours. Koko can decide her bananas per hour eating speed of K. Each hour, she chooses some pile of bananas to eat, and eats K bananas from that pile. If the pile has less than K bananas, she eats all of them instead, and will not eat any more bananas during this hour. Koko likes to eat slowly, but she wants to finish eating all the bananas for the guard's return. Return the minimum integer K such that she can eat all the bananas within 8 hours. Okay. So basically, if you go through a brute force type of a naive solution, you start from the beginning of the index. Obviously, we want to find the lowest k value, such that, which is the case of bananas per eating hour, such that Koko is able to eat all the bananas, right? You don't want to go too high, you want to find what's called a workable speed. And that's pretty much it. I mean, from the examples themselves, it's not very intuitive to see how you would get number 4 out of it. But so in the problem, Koko is given n piles of bananas represented by an integer, an array of length n. She eats bananas in a consistent speed, constant speed. So the speed we choose is not going to change from pile to pile. That means we have to generate one solution, right? So for example, she eats x bananas per hour, right? At k speed. Yeah. So the time taken to eat a pile of bananas is given by, let's say, so we see we have x bananas per hour, right? Bananas or b per hour, call that there. And then Koko takes the time. The time, let's say the time is um y, right? Y bananas is the x over y, where you take the ceiling of that, right? You take the ceiling of the round of that type of approach. Y bananas, which is the ceiling division of y over x, which is the rate. And then you round up to the closest integer. So if Koko eats 3 bananas per hour, then it will take her 2 hours to eat a pile of 4 bananas. That's just some math. Oh, by the way, this question is very it's kind of math heavy. So the first constraint of the problem is that Koko has to eat all bananas within 8 hours, where h is no less than the number of piles. So if you can imagine that with a fast speed, Koko spends 1 hour on each pile. Therefore, she can always finish all the bananas within 8 hours. However, this is called a workable speed, right? I mean, we want to find the minimum, and any number that's super high will work, but we want to find the smallest one. So, likewise, any smaller number other than that, that means that Koko cannot eat all bananas within the given time, and therefore that's called an unworkable speed. So we want to find the limit where it becomes unworkable, so that means she cannot finish all the bananas to the point exactly where she can finish all the bananas at a certain amount of k times, essentially. So that's basically what we have to find. So thinking about that, we have kind of if you use kind of a if you abstract the question here and the idea and the intuition, we can use a binary search to go about that, and it's not very clear that that's the case, but so we have to look for an efficient way of locating the minimum workable speed, eating speed. So we could calculate how the total time Koko takes to finish eating all the pods of bananas, but that will take a long time, right? That'll be done in a brute force approach. But we know 2 things is true from what we're given before. We know 2 things are true. I'm going to write some pseudocode here. So we know that if Koko eats all the pods of bananas with the speed of n, she can finish all the task within the speed of n plus 1. Right? So with a larger eating speed, Koko will spend less or equal time on every pile. Thus, the overall time is guaranteed to be less than or equal to that of the speed of n. So that means that if Koko can eat n bananas per hour, then this implies, or then, she could eat n plus 1 bananas per hour. Right? And that's true. Because if she n bananas per hour, then anything beyond that, she could eat all bananas, right? This is the... And then going the opposite direction. If she cannot eat n bananas per hour, then that means that she cannot eat n minus 1 bananas per hour, because anything less, then she won't have time to eat more bananas. That's pretty much it. So these are two truisms from what we gather so far from this problem. So how could we use this to our advantage, right? How could we kind of find right in the middle, the sweet spot of the workable speed, where Koko can eat all the bananas without spending too little time, which she cannot finish it all, or spending too much time with an n plus 1, right? We're going to find that n value that's the sweet spot. So let's develop some left and right boundaries. Say that we call this part, right, the right boundary, and this part the left boundary. If the current speed is workable, then the minimum work speed should be on the left, right, inclusively. And if the current work speed is not workable, then that is too slow to finish, so the Koko can't finish all the bananas. Therefore, the minimum work speed should be on the right, exclusively, right? And let's kind of go with that idea so far. Therefore, if we have two ends or two boundaries, we can use a binary search to locate the boundaries of the separate workable speed and the unworkable speeds to get the minimum number of workable speed, which is hopefully n. Right? Okay, let's find a reasonable upper bound or lower bound for the binary search. To ensure we don't miss any workable speeds, we are going to set the lower bound at 1 and the maximum bound no speed lower than 1. And the upper bound would be the maximum eating speed of the banana, and we know that, for instance, if the highest number, given, like, if you have, for example, we have 30 bananas in this, in the pile at I location, right? We know that the maximum boundary, the longest time it's going to take Koko to finish all the bananas is 30, because it's the maximum number of bananas per hour that she has, and therefore, ideally, it would be the maximum number of bananas she could eat. So that would be an upper bound and the maximum eating speed. And then once we set the boundaries, we're going to apply the binary search to reduce the search space. Which each iteration, we can just reduce the remaining search space by reducing it by half, since we already narrowed down to the one element we need. Therefore, we can find the minimum workable eating speed. So there's many other approaches to the solution, but here's one algorithm. What we could do is initialize two boundaries, the left and right equals 1, right? And let's just, I'll walk through the algorithm as we go along. So the first thing you want to do is initialize the left and right boundaries. We said before, left is going to be equal to 1, right? Which is 1 banana, right? If she eat 1 banana per hour, and if the pile has 1 banana, then we're golden. And then we're going to develop a right boundary, which is going to be the max value of our piles, right? Which is the highest amount of bananas in a pile. Yeah, that's pretty much left and right boundaries. Now we're going to develop our algorithm to get the middle value. And from the left and right, and Koko's eating speed during this duration is going to be the middle value between these two, hopefully for now. So in order to find the middle value, we want to do is get the, obviously whenever this is true, while left is less than right, we're going to try to get the middle index between left and right boundaries. And to do that, we do the, call this middle, and to find any middle number between two numbers is just left plus right divided by 2. That will be integer division. So we want a whole number. And then we want to find the rate that iterate over the piles. And then we could check to see if Koko can eat all the bananas within each hour given this eating speed. So we need to find the hour spent eating, and we could just do that and assign it to, well, the hour spent eating is not the same thing as rates as a rate, so we're gonna call this how to describe it? Call it K. Okay, I'll call it K. But we're going to assign that to 0. We have a rate of 0 so far initially. So we iterate through each of the piles and calculate the hours spent for eating bananas. And then we just increase the hour by taking the ceiling division of pile divided by middle. So we do a for loop here. So within the while loop, so for pile in piles, or banana piles and piles, we're going to find the hour spent, or K, the rate of what we each, and then we're gonna obviously take the ceiling of it. I'm gonna see if we could maybe math out ceiling. I don't know if ceiling is already included or not, but ceiling is a Python math function, pile divided by middle. And we take the float division here, and we take the ceiling of that to round up, and then we just update K, and then we add to it. So K will be incrementing by integers. So we want to check, now we know our boundaries and check for the middle. We want to check if the middle speed is workable, and then if it is, we can cut our search by half. So we can just reduce it. So this is to increase our space complexity or time complexity, one of those. Time complexity. So if K is less than or equal to H, so time spent in bananas, I'm not gonna call this K anymore. I'm gonna call this time spent. This K is a rate. We don't want to do that. Time spent is equivalent to hours, which is a lot better. And then we're gonna do right, assign right to middle. And then if it's not the case, then we want to assign left to be middle plus minus 1. Alright, that's pretty much it so far. And then we want to return our answer, of course. Return. Once the left and right boundaries have been are coinciding, so that means they meet each other at the same value, we can find our target value. That means that the upper, that's where the point where the upper unworkable, the workable rate, or the workable time, or was it workable? Is where the workable boundary, the workable speed, is equal to the unworkable speed, so therefore it's the max value we can get. Therefore, we want to return the minimum workable eating speed, which is going to be the same, either left or right. We'll just call it right. And then run the code. Wow, okay. Let's see what else I got wrong here. Side middle, right, spent for pile and piles. Take that if each middle that I see is plus 1. Alright. Yeah, it's plus 1 because we don't want to take the one less than it because it wouldn't make sense. Alright, there you go. Using a binary search. The question itself is it's a medium-sized question, but it's kind of on the challenge side. You need to know a lot of math for this, and kind of how ceiling division works, and a little bit more on, I guess, how to describe it. It's binary searching very in detail. It's a good question to really test your knowledge on this type of stuff. Alright, there you go. Have a great day, guys.